All right, in this video we're going to see how Newton's law of gravitation implies Kepler's second law and actually his zeroth law too, which he didn't write down, but anyway, here's the three laws. So these are all talking about planetary orbits. So the first one is that orbits are elliptical, and moreover that the sun is out of focus of the ellipse. The second one is that you sweep out equal areas in equal times. And the third one is that the period squared is proportional to the mean distance cubed. So anyway, we're not going to worry about these two in this one. We're just going to focus on the second law. And actually there's a zeroth law that people kind of recognize later, which is that the orbits are contained, or any particular orbit is contained in a plane. So, I mean, in principle, you could imagine the sun here and a planet going around and maybe going up and down, and it's, I mean, the kind of having a, maybe in addition to going around in a circle, there'd be superimposed a sine curve or something on top of it. That can't happen, at least according to Kepler's zeroth law, which he never wrote down. Actually, the zeroth law and all these laws are not quite true. And this was one of the things that really bothered physicists at the end of the 19th century. In particular, you have the sun here. Mercury, the closest planet, people notice, well, it more or less goes in an ellipse, but the plane that this ellipse is in is rotating very slowly at about 1 degree per century. And that was like one of the big problems that they didn't understand. So there was three questions at the end of the 19th century. Physicists thought they had the entire universe figured out. One was this rotation of the orbit of Mercury, and the other two had to do with quantum mechanics. One was black body radiation, and I forget the other one offhand. But anyway, this was one of the three things that they didn't know how to explain. And this one wound up being resolved by Einstein in his theory of general relativity. He showed that actually, well, according to his model, all of the orbits actually are the plane that they're in is rotating very slowly. It's the most pronounced with Mercury because it's the closest to the sun. But anyway, in this video, we're just going to use Newton's law of gravitation, which we recalled last time. FGMM over r squared, r hat, or this unit vector r hat can be written as the position over r. So let's do that real quick. This is minus GMM over r cubed, position vector. And of course, we know Newton's second law, that F equals ma. And so there's a lot there. And we're not going to use hardly any of it right now. So to get Newton's, or not Newton's, but Kepler's zeroth and second law, all we need from this entire equation is that A is parallel to R. So this is just some scalar, that's a scalar. So this says A is a number times R, right? And we saw in one of the earlier videos, how do we make use of, if we know two vectors are parallel, what's kind of the first thing we like to write down? Well, the first thing we like to write down is that if I take their cross product, I get 0. All right, so that's all we're going to use. Well, let's go ahead and see what we can get out of that. So, kind of inspired by this, I'm tempted to take the derivative of r cross v. So again, I'm saying, so the derivative of r, I'm calling velocity, and then derivative of velocity is acceleration. So if I take the derivative of r cross v, well, my product rule works for cross products just like for regular numbers. So the derivative of r is v, and then leave the second one alone. And then my second term, I'll leave the first one alone and take the derivative of v, which is a. Okay. And let's think about this. Well, v cross v, we know this is always 0 because any vector across itself is 0. So this is always true. And we just saw that by Newton's law of gravitation, r cross a is also 0. So this is by the law of gravitation. So we have the time derivative of r cross v is 0. And another way to say that is that r cross v has to be a constant vector. All right. Well, actually, that right there, if we look at the direction part of that statement, we get the 0th law. If we look at the magnitude part of this statement, we get the second law. So let's talk about the direction part first. Well, so let me kind of draw a picture of going around in a circle. So you've got your R and your V there. Or over here you've got, say, R and then V. Or over here you've got like R and then V. So R and V are definitely changing as this is going on. But it's saying if you take their cross product, it's always the same. Well, what do we know about the direction of the cross product? It's perpendicular to the vectors that we started with, right? So if I take, say, these two R and V versus these two R and V, well, when I cross product them, I get a guy sticking straight out. When I cross product these two, I get a guy sticking straight out. I mean, the only way that this direction of C isn't moving is if my R and V have to stay in the plane. That way, C is always sticking like straight out of the board. I mean, if R and V were to change and like say so suddenly maybe R is going straight out, but V is kind of pointing into the board a little bit, then all of a sudden my C would be in a different direction. The fact that C is not changing its direction means R and V have to stay in the same plane. Okay, so there's the 0th law. And now let's look at the magnitude. Well, let's draw a picture to try to figure out what R cross V means in terms of magnitude. Well, here's R. Let's say I move a very short distance, so I might not move perpendicular. So this is dr. And let's think about this triangle. Well, we already saw this in the homework that the area of this triangle, so we'll call that dA, is equal to the magnitude of the cross product of those two vectors divided by 2. Like if I didn't divide by 2, I'd get this whole parallelogram, and dividing by 2 gives me just that triangle, right? Well, what have we got here? Well, that's dA, so if I look at dA dt, that would be 1/2. I mean, dt is just a positive scalar. I can push it inside the norm of this vector, so this is norm. So if I have a scalar like dt, 1/dt times this scalar, I can move it inside. So this is 1/2. Okay. this r infinitesimal, I mean, it's fixed. We're just looking at the change. So this is dr dt. So I'm kind of being a little physicist about this argument. I mean, really, you would have to be a little more precise. But I mean, but that's the point, is that if I look at dA dt, it is just the magnitude of r cross v divided by 2. And again, since r cross v is constant, I get that dA dt is constant. So if I take a particular length of time, it doesn't matter what that time is. So the change in area only depends on change in t. I mean, whatever this constant is, you'll have delta A is that constant times delta t, right? So, yeah, so the change in area only depends on the change in time, which means that if I don't have a circular orbit, so that is Kepler's second law, by the way, which means if I don't have a circular orbit, well, here, I mean, because this is very, very long, and whatever, say this is like 1 month of the orbit. That's a pretty big area. I've got to get the same area in 1 month on the short side. So since it's so much narrower, it's going to have to be a lot wider to make up for it. So this would have to be like a month like that. So we have to have the same area as long as we have the same time, right? Which means that I have to be going a whole lot faster when I'm close to the sun than I do when I'm at the other end of the orbit. So anyway, so that's where Kepler's second law comes from, and his zeroth law. Again, they're both just simple consequences of r cross v is constant, and that in and of itself is a consequence of A is parallel to r. So anytime you have the acceleration is in the direction of position, so here's the separation vector. Anytime the acceleration is in the same direction as this position vector, you're going to have the zeroth and the second laws, where all the motion stays in a plane and that motion sweeps out equal areas and equal times. And then in the next video, we'll use more of the law of gravitation and show that in this case you actually get, well, I say an ellipse, but it really could be any conic section.